From MIT PhD to AI startup founder, Chenru Duan and his colleagues discovered that current AI benchmarks aren't really measuring how real scientific discovery actually works. Here's his story and what he and his team are building to fix this problem. So thanks for joining us today. I think you have a really interesting career path already, and you're sort of just getting started. So maybe you can tell us a little bit about your journey from academia to industry, and now to the startup. But interested to hear about your journey.
Yeah, so I did my undergrad actually in Zhejiang University in physics, where I found like the theoretical physics a little bit too difficult to me to understand the quantum field theory and everything like that. And well, I did some research in physics, but I find like it's a little bit disconnected to the real world. So I applied for chemistry when I graduated. And very luckily, I got into MIT and I met with my PhD advisor, had a colleague who had an interest into like applying machine learning to chemistry problem. So we started I started the journey from there in 2017. And I explore a lot of work, I think, in the application between machine learning and computational chemistry. So starting from how we can incorporate machine learning models to do decision making in high throughput computation, and to the optimization process of discovering new functional materials, specific transition metal complexes. And I think at most of the time during my PhD, I aim for an academia position. It is mostly because that's the path that I'm mostly familiar with. At that time, I don't know that much about the industrial world because like I'm immigrant and I'm just got to the MIT environment, which is full of enthusiasm about academia. But I think things changed in 2021, where me and some of the friends starting to organize the AI for Science workshop in a series of machine learning conferences, for example, ICML and NeurIPS. And at that time, we basically get in touch with the industry community a little bit more because we have to raise funding to have those workshops. And at that time, I talked to folks at like DeepMind and Microsoft about how we should set up this workshop scenario. And it's quite interesting to work with them. And at that time, DeepMind also just released the AlphaFold 2, which I think is really a milestone in AI for Science. So I started by talking more to them, I'm starting to realize that probably industry is also a good path for PhD students working on AI, on the intersection of AI and science. And I just learned more about that path. And eventually, I think like when Microsoft started to launch the AI for Science initiative, I'm fully convinced that industry is at least a better option to scale up the technique in the domain of AI for Science. That's why I joined Microsoft, where we did a lot of interesting work about building a new platform called Azure Quantum Elements, basically an integration of tons of different AI for Science algorithms, such that we can basically package them all together to connect to like big customers in chemistry and materials sections, and then like doing service with them and helping them to develop their own pipelines. I think that's great experience where I learned learn a lot about how we can basically do research in big tech and how we should talk to customers and get the deal eventually signed. And I think the inspiration about getting started a new startup of our own kind of starts with the fact that we realized, at least I realized at that time, that like platform that like in the field of AI for Science, there's a still gap between the real production. For example, like if I build an AI for Science algorithm that I think is, let's say, it worth 80, when we deliver to the customer because they're less experienced as we do in terms of the AI, like you probably can use it only to the score of 60 or even less. So how we can help them in a way to build better chemistry. I think the way that we wanna, but like as a big tech of Microsoft, it's quite difficult for them to set up a structure that we can help each individual customer and solve their problem in depth. So like this kind of, I think the contrast inspired us at that point to set up the new startup that I'm the founder and CTO of right now, like Deep Principle, where our aim is to work with the customers directly with AI for science algorithm or experiments, whatever it takes, simply to build better chemistry using chemical reactions. So that's kind of the goal of the company, and that's also the journey that I take on this path.
Yeah, it's a really interesting journey, and I think you highlighted Microsoft and Google, and there's also NVIDIA and many other players in this space. But this is an area where you didn't really hear of anybody from the material science or chemistry communities going into those companies before 2021 or somewhere around there. Maybe it was a little bit earlier than that, but it seemed like those efforts really scaled up. So I wonder if you have any questions or some thoughts about things that you learned in industry that could reflect back to improve academic research.
Yeah, I think there were a lot of, like, for example, I would just take Dow Chemical as an example on the other side, where it's a representative like giant in chemistry and material industry who really want AI in their pipeline. The way that they do is mostly to collaborate with people in professors in academia. So I know Heather once had a grant with them working on like AI accelerating catalysis discovery. I think that's the way that they do it. But because like there's a really long pipeline between discovering the material to that it can be made in the lab and even to the final production. So it's really hard that for people in academia to directly get into any skill that pass beyond the lab skill. I think that's essentially the nature of chemistry and material industry, and there's nothing wrong that people in academia cannot solve the problem in production because that's not the goal of academia. I think people should keep innovating in terms of new algorithms, discovering new material, finding new chemical mechanism, such that it may have longer impact on the whole industry. I think that's what they should. Like, I think that's the initial purpose of the academia in that field. But I think for AI for science, it's a little bit different. At least for me, I take this as a 10-year opportunity that in my lifetime that I can do something that probably meaningful, like in my 30s. That's really the reason why that we want to jump out of the academia and try to fulfill that in this short time period.
Great. Yeah, it sounds like you've been very successful raising your seed round with Deep Principle. What are some things that you're most excited about solving via Deep Principle? What are the problems that keep your customers up at night, and what are the solutions that you all are bringing to the table here?
I think the most exciting thing that I have like during this journey is that we can really work with our customer hand in hand, such that we know exactly what their problems are, exactly their experimental data, and the bottleneck that they have in their production, all the lab skill, and we can work with that problem more directly, such that we can see where we can make an impact of AI for science. Because like no matter what are done in terms of like academia, no matter what type of problems that we solved in academia, there will always be a gap between that to the real industry. But working on the real industry people and having the potential impact about the industry and bringing value that excites me. Like, so for example, like the two roles that we're pursuing with our customer is first the diffusion model on generating chemical reactions such that we can basically avoid some of the side reactions or improving the yield and selectivity of the main reaction, etc., as well as using the LLMs to help them to kind of solve some of the industry problem directly. So like those two mainstream of the research in generative AI, I still see there's a need and that it can be directly helpful in solving customers' problem. That's also one thing that makes me very exciting about. So people are going beyond the Bayesian optimization, design of experiments, VMs, or like small, fully connected neural network, and using real generative AI to solve their problem.
Great. And I think that sort of brings us to the next topic, which is, we really wanted to talk today about the scientific discovery evaluation framework. And it's obviously the topic of the last few years has been, what is the effect of AI going to be on science? And lots of people are assuming that AI will accelerate the research process, but, it's always a question of like, how do we measure that? And as we know, there are many tests and benchmarks that have been used for the models that people are familiar with, like OpenAI and Claude models and others that test for capabilities in math or coding ability. Also, many more benchmarks than that. But I think there's still an opportunity in the space of understanding their capabilities in scientific discovery, in terms of hypothesis generation, in terms of actually doing creative work in science. And so I know you and some others are working on this. Maybe you can tell us a little bit about the scientific discovery evaluation framework, which we can just call SDE or SDEF. Tell us about that, and if you want to show off some of the capabilities, that would be great as well.
Yeah, I think that's a very interesting point, and about like having, I think like there's a huge distinction between general science problems and scientific discovery. So I think like people, if they were young enough that can still recall the time that they take classes, they will still remember that like learning textbook example is quite different from doing research, because like research is more scenario based, that you need to like link from what you see, the direct problem that you need to handle and provide a solution, or you need to do hypothesis generation, as you said, then for iteratively improve the observation. So I think of course there are a lot of like different benchmark has already been created. There were GPQA by Google very early on, and I think recently there's humanity last exams, which also covers a series of science problems. I think very recently, Andrew White actually, like from Future House, he curated the data set and found that a lot of the questions, I think 30%, are kind of invalid. I think we also look into that and find a similar problem. And there was a Nature Chemistry paper. They do a series of chemistry tasks, but that's limited to chemistry. And I think still were under the domain of general science rather than scientific discovery. So I think the idea that we have is twofold. Yeah. First, we want to create a layer, like the top-down breakdown between domain, for example, from chemistry, materials, biology, physics, and then to the concrete research problem. So for example, I want to synthesize new molecule that achieve this functionality. I want to solve this quantum field equation with LLMs, etc. And then we choose from the project's end, we break down to specific tasks. So for example, after I synthesize a new molecule, I want to do NMR, and through the NMR spectroscopy, I want to back out what the molecules that I synthesized was, so that I can basically reiterate and improve the synthesis procedure. And from that NMR to molecule tasks, I can basically create a series of questions. So we want to really have a connection between projects, tasks, and questions. That's what we want to do to establish a new standard in scientific discovery evaluation. For the questions, I think it's quite straightforward, where we can use some existing code base to do that. One thing that we use, I will share the screen now. So this is actually the code base that like people have been using a lot in testing the evaluating LLMs in terms of normal Q&A type of questions. So basically, they have a series of functions to call different LLMs and then recall the findings, etc. Basically, it's a very complete suite of evaluation functions and utility functions so that people can test LLMs on different benchmark data sets easily. But what we don't have is a counterpart for scientific discovery. And this scientific discovery process cannot be directly fit into this LLM evaluation harness progress, because it's not a simple Q&A. And in scientific discovery, we usually require a iterative process, starting by anything like in this loop, for example, starting by the hypotheses that are generated by either human or, like, since we're talking about LLMs evaluation, probably by LLMs. And then like people will do simulations or experiments to verify this hypothesis, such that we'll have new observation and data. And by getting those new observations and data, we will basically improve or at least change the hypothesis, which require close the loop. And then like this loop just goes on and on to until some new discovery can be found. And this loop cannot be directly fit into the LLM evaluation harness, which is why, but like this is a very generic scientific discovery loop. I think if you look at every single research paper, that will basically behind this thing story for them, no matter you're finding new photocatalysis or getting the new battery materials. Sometimes it may not directly be reported in the paper, but I believe that's something that have been happening under the scene. So from that, I think Ben, you also have experience about organizing the hackathons. I don't know how exactly people are doing, but I think from the most recent report that I see from Archive, people are still doing a lot of heuristic stuff using their own handcrafted code. That's also one of the motivation for us to basically create this new unified code framework that hopefully can be applied to every single scientific discovery workflow. And it's quite simple that follows the scientific discovery loop. So we will hopefully every single problem can be fit within the scope. And what we do is basically provide support function or utility function, as well as some simple classes that hopefully are general enough that people can use. So for example, we have four core components or classes that we build. The first is a generation class. This is something that quite ubiquitous also in the LLM evaluation harness project. Basically, it's a class that helps us to communicate with LLMs, and we use light LLMs to centralize all the communication so that it's easier for us to basically use all types of different models and synchronize those parameters. And we also have async batching processing, but for the advanced use cases. And then we have the prompt class. That's exactly the that basically incorporate all the details that we want to communicate with LLMs. For example, it has a lot of different templates, which we kind of summarize from a series of research projects that we're currently implementing right now. For example, summarizing the previous historical conversation and simple Q&A type of questions, and future learning, iterative learning, as well as iterative learning with feedback, etc. So this is a class that basically help us to create a prompt in a systematic way. And this prompt class can, however, can of course be extended into different type of scenarios, if needed. And the third is the evaluation class, basically, which we call as Oracle, that usually incorporates two things. The first is the matrix, because when we have the scientific discovery project, normally we want to develop a metric that is either a traditional single round metric to evaluate on individual outputs, or we want to have the multi-round metric. Basically, we want to see how things evolve across multiple iteration. And from that, we will basically observe. That will basically lead as a evaluation process for the observation that we made that are generated from the LLM's hypothesis. And the last part is the workflow class. The workflow class basically chain everything together in a loop. It's quite simple that it basically first construct the prompt. Secondarily, it put into the generation class that I introduced in the beginning, and then it call LLMs, and then provide the evaluation using the Oracle class. And lastly, it will just repeat by the new from the beginning to generate the new hypothesis. And this is basically one example for doing that. And of course, we have a ton of advanced features that enable, for example, async running. Basically, that's the batch option, as well as the complete record using V, so that we can basically dig out all the historical information that we have run via any of the LLM's requests. So this is the basic setup of this repo. And in this repo, we also provide a series of basically quick implementation guide about how one can start a very simple project from scratch. I think that will be helpful if people like that participate in the hackathon, they have some great idea to start, and they probably can follow the development logic of this repo, or at least use the utility function there so that they don't need to care about how to record their LLM responses and how to like basically call the LLM. So that will hopefully be helpful. And we also incorporate one demo project at this point. People is still going on in terms of implementation about using LLMs to do evolutionary optimizations on transition metal complexes. So basically, this is a repo that we turned from our original work under and adapted into this SDE Harness code framework. So I think it only takes with Cloudy Code, I think 1 hour to finish everything. So it should be very simple to like depends on the code quality that you originally have, but it should be quite simple to adapt your original code into the new code framework, especially with the help of the current like AI coding tools. I think that's all I want to introduce for the code repo. Yeah,
Great,
and hopefully people can enjoy using this for sure.
Yeah, it looks like a great tool. I'm curious if it looks like there's an example set there as well. So if people go to that repo, they'll see I forget what it's called, LLM as one example, and then they'll see an examples directory that maybe has some other examples to get started. If there's a team that's just doing something very simple, it sounds like their first place to go is that markdown document that explains here's the quick start of getting ready to get going.
Yeah, exactly. And I think as long as it follows the scientific discovery loop, it should be very natural to incorporate into it. So basically, it's just an upgraded version of LM evaluation where we're not only taking care of the simple Q&A, for example, the hypothesis generation part, we chain it from the data set as well as the observation class such that it form the final workflow class in the end to do the materials optimization.
Great. Yeah, it seems like a very useful tool. We hope that maybe you or some others from your company can participate in the hackathon or stop by. So yeah, thank you for taking the time today. I know you're very busy and visiting the East Coast and with the startup, right? So thank you for taking the time. I really appreciate it, Chenru.
Yeah, thanks, Ben. And lastly, I have to add that like this is not the effort from the company alone. So we have a very huge team from different organizations and university to basically set up the scientific discovery evaluation benchmark as well as implementing the code base. So it's actually a team effort. Preparing a paper hopefully will be online in October, and at that time people can see the entire team.